Welcome to my video. My name is Yaqub Aliyev. I am from Media University, Baku, Azerbaijan. I will talk about the best constant inequalities and their applications. First of all, the inequality. Let us consider this inequality, the sum of reciprocals of n numbers is greater than or equal to lambda divided by 1 plus n to the n minus 2 lambda minus n squared, product of these n numbers. Here, all the numbers xi are taken as positive. Their sum is taken as 1 for simplicity. And we assume that n is greater than or equal to 2. Here, lambda is a real number, parameter, and it is asked here to find the best maximal possible lambda for each n. This problem appeared in the problem corner of research group in mathematical inequalities and applications in 2009. Let us look at the right-hand side of this inequality closely. So this function is a non-decreasing function of lambda greater than 0. We are interested only with positive lambda. So if our inequality 1, is true for a certain lambda equals lambda sub 0, then it is also true for all smaller lambda 0 positive. By Cauchy-Schwarz inequality, the sum of reciprocals of this n numbers is greater than or equal to n squared. On the other hand, if you put lambda equals n squared here, you will obtain again n squared. Since the inequality holds true for lambda equals n squared, it also holds true for all smaller n lambda less than or equal to n squared. So if the best constant exists, it should be greater than or equal to n squared. This can be interpreted as lower bound for that best constant. Let us start investigating this inequality case by case. Let us start with the case n equals 2. N equals 1 is a trivial case, so I will not discuss it here. For the case n equals 2, there is no best constant. Indeed, we obtain this inequality. Here, x1, x2 are positive, sum of x1 and x2 is 1. You can check that this inequality is true for any lambda greater than 0. Let us do this together. Indeed, if we multiply both sides by 1 plus lambda minus 4 x1, x2, this denominator, then we obtain this inequality. But x1 plus x2 is 1, so lambda cancels out from these two sides, and we obtain this inequality, which is always true. So it doesn't depend on lambda, it is always true. Interesting cases start with n equals 3. For the case n equals 3, the best constant is lambda equals 25. Indeed, we will obtain this inequality where x1, x2, x3 again are positive, sum is 1. This inequality is true only for lambda less than or equal to 25. Indeed, if we will substitute in this inequality x1 equals x2 equals 1 over 4 and x3 equals 1 over 2, we obtain that lambda should be less than or equal to 25. On the other hand, if we will put lambda equals 25 here, we will obtain this inequality, which can be proved. This inequality appeared in American Mathematical Monthly in 2006. There are some nice geometric applications of the case n equals 3, and these are one of the reasons why this inequality is interesting. So this inequality, r over r greater than or equal to 2 times mu multiplied by this positive number, where r and r are respectively the circumradius and inradius, and ABC are the sides of a triangle. This inequality holds true for mu less than or equal to 8. Indeed, if you will take this triangle with sides 3, 3, 2, then the corresponding values of the circumradius and inradius will be 9 over 4 divided 4 times square root of 2 and square root of 2 divided by 2. And if you will put all this into this inequality, you will obtain mu less than or equal to 8. Again, if we will prove 2 for mu equals 8, then mu equals 8 will be the best constant for this inequality. When mu equals 8, we obtain this inequality, which is, by the way, a refinement of Euler's inequality R over R greater than or equal to 2. And it follows directly from the case n equals 3 in our inequality. Note that equality in this triangle, in this inequality, occurs when the triangle is equilateral, but not just this. The equality occurs also for the triangle with sides 3, 3, 2. This triangle is not so special in geometry, but here we have it is nice property of corresponding to equality cases of this inequality. This inequality appeared in 2009 in La Gazzetta della Real Sociedad Matematica Española as a problem. Another interesting geometric application of the case n equals 3. If A, B, C are the sides of a triangle, then this inequality holds true, and it is a sharp inequality. In a certain sense, one cannot improve these constants here. This appeared in the paper from 2009. One more geometric application of the case n equals 3. We need some notation to write this application. Let M be a given point in a triangle. Extend the lines AM, BM, and CM to intersect the sides of the triangle ABC at A0, B0, and C0 respectively. Next, construct a parallel to A0, C0 through M, parallel to B0, A0 through M, and parallel to B0, C0 through M. They will intersect the sides of triangle at some points, and we will obtain triangles whose areas we will be denoting by these letters. Let me show you all this on a picture. So we choose arbitrary point M inside of the triangle, draw AM, BM, CM, which intersect the opposite sides at A0, B0, C0. Then draw this line through M parallel to A0, B0, line parallel to B0, C0 through M again, line parallel to A0, C0 through M. These lines intersect the sides of the triangle, but at these points, B1, B2, C1, C2, A1, E2. And we obtain these triangles. We denote the areas of these triangles by these letters. Then this inequality holds true. P1 plus P2 plus P3 plus 7 times S1 plus S2 plus S3 greater than or equal to 8 times T1 plus T2 plus T3. Again, sharp inequality, which cannot be improved in a certain sense. This appeared in problem-solving journal, Crux Mathematicorum with Mathematical Mayhem. So, we are motivated to study this inequality. There are nice applications in geometry. Let us now consider other cases, the case n equals 4. For the case n equals 4, the best constant is lambda equals this number, which is approximately 30.4. Indeed, we obtain the inequality, this inequality for 4 numbers. This inequality is true only for lambda, which are less than or equal to this best constant. We can check this by substituting x1, x2, x3 with this number and x4 with this number. Their sum is 1. We will automatically obtain lambda less than or equal to this best constant. On the other hand, we can prove this inequality for lambda equals this best constant. Therefore, this number is indeed the best constant for this inequality. It is maximum possible value for this inequality. We heavily used Maple to find this number and prove it. It appeared in 2007 in Journal of Inequalities in Pure and Applied Mathematics. Let us now look at all cases n greater than or equal to 3 from a unified way, in a unified way. We can rewrite our inequality in this form. Let us take any 3 variables from the set x1, x2, xn, any 3, and denote them by x, y, z. Let us assume that x, y, z and x plus y plus z are constants, so they don't change. While keeping these two constant, we want to minimize 1 over x plus 1 over y plus 1 over z to determine the best lambda in 3. So this 2 doesn't change, the sum doesn't change, only this can change. We want to minimize this. Minimization of this will also minimize the left side of 3, and we can therefore find the best constant for this. Noting that 1 over x plus 1 over y plus 1 over z, using the conditions for x, y, z, can be written like this. If you will consider this as a function of x, then its derivative is this. And assuming that derivative is equal to 0, because we are interested with critical points, we obtain this equality, which after some transformations come to this. And this is equivalent to say that either x equals y or x equals z. These two can also be true at the same time, so all of them are equal to each other. X equals y equals z. Therefore, the left side of 3, the previous inequality here, is minimal only when there are at most 2 distinct numbers in the set x1, x2, xn. Consequently, we can restrict ourselves only to the cases when k of the numbers x1, x2, xn are equal to x, the rest of the numbers are equal to 1 minus kx divided by n minus k. We assume that k is from 1 to n minus 1. Because of symmetry, we can restrict k to this interval. And x will be taken from the interval 0, 1 over k to make sure that all the numbers x1, x2, xn are positive. We can now put this in the inequality 3. For this, we will first change 3 a little bit. We will obtain this inequality. And let us denote this part of this inequality as gkx. K is an integer, positive integer, x is a variable. X changes in the interval 0, 1 over k, k changes in this interval. We can easily see that this function is not defined at 1 over n, but we can find its limit as at 1 over n. When we find its limit, we observe that it is not even dependent on k, which is surprising. We can use L'Hopital's rule for this purpose, and we find that the limit of gkx is 2 over n, which means that the best constant, lambda 0, will be less than or equal to n squared divided by 1 minus 2 over n, which we can write like this. The left side, there was also lower bound, which we proved earlier. So we obtain this double inequality for the best constant. It is between n squared and n cubed divided by n minus 2. Numerical experiments for large n with maple show that the upper bound is quite good, but the lower bound needs some improvement, which I couldn't do, unfortunately. Even for smaller numbers, for which we know for sure that lambda 0 is 25, this is case n equals 3, and lambda 0 equals to approximately 30.4 when n equals 4. This double inequality gives quite good approximation from above. Indeed, n cubed over n minus 2 when n equals 3 gives 27, and our best constant was 25. For n equals 4, 4 cubed divided by 4 minus 2 gives 32, and the best constant was 30.4. So it is quite good approximation. Now we can say something about the case n equals 5. For the case n equals 5, we obtain this inequality, and using Maple, I found that the best constant is this number, which is approximately 40.09. Equality cases in this inequality occur, of course, when all of the numbers are equal to 1/5, trivial case. And when, for example, x1, x2, x3, x4 are equal to this number, which is around 0.173, and x5 is equal to 1 minus 4x, it is to complete it to the sum 1, 0.308. Again, Maple was heavily used here to prove all these results. Some open questions. The case n equals 5, which I have just shown you, is probably the last case for which we can write a nice formula for the best constant. For greater values of n, it is reasonable to focus on asymptotic formula of the best constant. We propose some open problems that can help with this idea. Prove that lambda 0 is approximately n plus 1 squared when n goes to infinity. There are also better approximations that I found experimenting with Maple. Lambda 0 is approximately equal to n squared divided by 15/8n. To prove these results, one might need to solve also problem 2, which is a little bit technical. Prove that if k is in this interval and x is in the interval, then gkx that I introduced earlier, or left-hand side of 4, attains its minimal value when k is n minus 1 and x is between 1/n plus 1 and 1/n. The solutions of these problems will give us better understanding for how lambda 0 changes as n tends to infinity. This is my last slide. I just wanted to mention that there are similar inequalities in the literature. For example, one can find this inequality in the literature for which the best constant is known for all n. It is n squared minus n to the n divided by n minus 1 to the n minus 1. It is possible to write an asymptotic formula for this. In particular, if n equals 3, then the best constant inequality is this, which appeared several times in mathematical Olympiads, which in turn is equivalent to the geometric inequality. P squared is greater than or equal to 16r multiplied by r minus 5r squared, where P is the semiperimeter of the triangle. R and R were introduced earlier. But this inequality is easy because it follows directly from the formula for the distance between the incenter and the centroid G of a triangle. There is a formula in geometry books for this distance, IG squared is equal to this. So the inequality directly follows from. More about this inequality from in the Mitev's paper from 2003. I want to show also my calculations in Maple. So I used solve in Maple to find those best constants. So here the lambda was replaced by f. So I solved it for f to find this function. Then to find it as critical points, I differentiated it, made it equal to 0, solved it to find this root. I am interested with this real root. And then I put this number back into the function to find that best constant. It is approximately 40.09. And that's, I think, all. Thank you for listening.